So let me get this back to the start. So where we are, we're doing, this today is Net Plus. So hopefully you guys already know this stuff, and this is review. Like I say, that's why the CISSP is fairly easy for us, because most of it is A+, Net Plus, and Security Plus. Only about a third of it, or quarter of it, is management stuff, which is new to us. The poor managers, 3/4 of it new to them. So this is network architecture and design, which is basically Net Plus. So when you communicate from one device to another, simplex is the old-fashioned communication where you can only go one direction, and that's it, like broadcast television. You can receive, but you cannot send. Then there's half duplex, where you can go one way, but only one way at a time. This is the old walkie-talkies, where one person can talk, and then you say over, then the other person can talk, then you say over, and you take turns doing that. Full duplex is what we want, and what almost everything is now, where both people can talk and listen at the same time in both directions. Baseband is where you take the entire frequency range available on the transmission medium and use it for one signal. This is how Ethernet works. You have an Ethernet cable, and there's one computer at each end, and that's it. They have access to the entire bandwidth of the cable. Broadband is what you have on going through the air, where you have only like AM radio or your Wi-Fi, you have only a channel, and you have only a frequency range for one channel of communication, and the other frequencies are being used for other communications, so you have only a limited bandwidth. Analog is data sent through something like sound, like I'm talking right now, making pressure waves in the air, and it is not digitized. It's just a smoothly varying signal. This is the way all natural signals are, and the problem with it is that it is distorted as it is transmitted and received, and there is no way to ever fix that distortion. Because you have no way to tell what the original was. The advantage of digital signals, where you take an analog medium and then you artificially call some region 1 and some other region 0, and you make a signal that tries to go back and forth between them, so you waste most of the transmission ability in the analog signal and cut it down to just ones and zeros. But the point is, now you can put checksums in your packets, so you can detect when they're damaged and resend them, and know that you get 100% perfect transmission, because you can detect and fix errors. And that's why digital transmission, which is intrinsically wasteful, taking an analog reality and forcing it into a digital reality, which seems inefficient, but the end result is now you can have perfect copies and perfect transmission. This is why the digital revolution is kind of nuts and involves getting less than you could get out of the hardware. And that's why quantum computing is the giant leap forward, where instead of doing this unnatural thing of ganging electrons together by millions and having all these millions of electrons move one way and call that a bit, you now go back to letting every single electron do what it naturally does and exploit that. So now if you have a million electrons, you have a million processors doing something, instead of all of them being forced into a bucket to pretend they're a 1 or a 0. Anyway. All right, so LAN is the network within a building typically. Metropolitan area network goes in a city, wide area network goes anything bigger. The internet is the largest possible WAN covering the whole world. And there's a personal area network, which are the devices on your body typically connected by Bluetooth. So the internet is the global connection of all the networks running TCP/IP. There have been other networking protocols like AppleTalk and IPX, but they've pretty much all gone the way of the dodo bird, and everything is pretty much TCP/IP now because of the internet. You can have an intranet, which is a privately owned network where it uses the same protocol, but you have to be a member of the authenticated as a member of the company to get in, and they don't let the whole world in. This is what people are calling the private cloud these days, where you have servers that are available to your employees but not to the whole world. An extranet connects private internets, connecting business partners together, like the way Home Depot got hacked through their air conditioning supplier. I think that was the one. So circuit switch networks are the original old-fashioned ones, where they had operators with a bunch of plugs, and you would want to make a call and they would put in a plug, and now you have one physical wire connecting you to the other person, and it's all yours for the duration of your call, and then they pull the plug and give that wire to someone else. This was extremely inefficient because most of the time the wire is not carrying anything, so it's much better to do packet switch networks where many people can share the same physical wire by just labeling and addressing their packets, and now one person's packets go through, and when they're done, another person's packets go down the same wire. Quality of service is necessary if you're going to have a shared line, so you can prioritize traffic. For example, voice traffic has to have high priority because a delay of even 50 milliseconds in a voice makes it hard to understand. Whereas a delay of 100 milliseconds in an email doesn't matter, so you prioritize it, and that's what quality of service does. In order to make it practical to manufacture hardware and software and sell it and have it interoperate, so you can have an Apple computer and a Cisco router and, you know, cable made by some other company and everything, everybody has to obey standards. Let's see if I can figure out how to attach this thing so it won't fall off. All right, so that's what these layers do. You define little pieces of the job to be done, and you can manufacture hardware and software that does just one component. This is the same thing as structured programming, where you have a function, and the function does just one thing. And then the function can be reused in different environments. So you have a network model. These are theoretical, sort of mathematical models for what functions should do, and real hardware and software only approximately follows them. The actual hardware and software pretty much follows the 4-layer TCP/IP model, but the most common theoretical model is the European OSI model with 7 layers, of which only 4 are actually real in most cases. So this is the 7-layer model. All people seem to need data processing. Please do not throw sausage pizza away. These are the layers from the bottom to top. The 4 layers are absolutely real, and you'll see the addresses in Wireshark. You have the physical connection between the cables, you have the data link connection with MAC addresses, you have the network connection with IP addresses, and the transport layer with ports, TCP and UDP. These 3 layers above there are mathematical abstractions and usually all combined in the same piece of software, like your browser doing all 3 of them. And rarely are they really distinct. So the physical layer has, the layers also have protocol data units, which is the name of a data there. The physical layer carries bits in, say, pulses of light through fiber optics or radio or Ethernet pulses of electricity. And hubs, repeaters, and cables are all layer 1 devices. They simply move a signal from one place to another without reading addresses or understanding it. They just amplify it and send it down the wire, and it's carried by the electrical properties of the wire without being addressed to anything in particular. Layer 2 is the first area where you have some logical addresses. These are physical addresses. And these Ethernet card, everything sent on a network has to go by MAC address. All IP addresses have to be resolved to a MAC address before anything can be delivered. So that's Ethernet, and Wi-Fi uses an address that's very similar. So that's the game. Your switches, bridges, and Ethernet cards are smarter devices that actually know the MAC addresses and therefore only send packets in the right direction to reach the right device, as opposed to hubs that just spit packets all over the place. The data link layer is layer 2 with 2 sublayers. Media access control connects to the layer below. Logical link control connects to the layer above. And people rarely bother with the distinction between those. Layer 3 is the network layer using IP, and this finds the physical location of the destination. This is what makes the big distance hop from one nation to another, from one city to another, to find where your device is. So it has to have the public IP addresses that are like phone numbers. Only one computer in the whole world can have one public IP address under normal circumstances, unless you use Anycast, and that's what routers do. They make the big distance hops. Once you reach the right physical device at the other end, now you use the transport layer to specify which process you want to talk to on that device. So if one server is doing email and web pages, you use the TCP port to tell you which one of those you're talking to. TCP is reliable. Not that it is more likely to send a packet without an error. It just detects errors and prompts retransmission. So that's what reliable means. Reliable means you know when an error happened and you retry as long as it's possible to get it in. UDP is not reliable. It is just best effort. If a packet does not get there, no acknowledgement comes back and the sender never knows it and nothing is ever fixed. The session layer is where you have a more abstract concept, like say you have logged into a server and now you have access to the network shares. This is a layer 5 concept. It's beyond finding the right device and beyond finding the right protocol at layer 4. It's something else, like you've logged in and now for some period of time you are authorized to do something. That's a layer 5 session concept. You established a session. Then there's the presentation layer, where you rearrange data to make it more comprehensible. There's things like turning ASCII into printable text, changing GIF and JPEG formats into something you can see, encryption and compression. Those are at layer 6 activities. And at layer 7 is where you hand it off to the user. This is where you get input from the user in human-friendly things like a browser or an email client where they can see things they understand and click on links and such. And so this is where Telnet, FTP, and HTTP are in the application layer, and they all use all the layers below them. So I've got a few cahoots about that stuff. What transmission goes through an Ethernet cable? Okay, that's baseband. All the bandwidth is reserved for one signal. All right, what OSI layer uses MAC addresses? Layer 2, good. All right, what layer has hubs? Okay, that's layer 1. All right, and where are the network file shares? And that's definitely 4 or higher. There are different ways to look at it. You could call it layer 7, you could call it layer 5, but anyway, it's up there. All right. And that's not right. I should have you see. There we are. Now I can see 3 people. Okay. So E, I know who that is.
Yeah, it's close.
Password, that's you, right? Okay, good.
Too many easy ones.
So there's how the two models compare. The TCP/IP model combines data link and physical into network access, internet for network, and transport for transport. And those are the 3 with addresses, MAC, IP, and TCP. And everything above it, they just call it application. And like I say, that is the way real software is mostly. The distinction here is mostly theoretical. But anyway, that's how the two models match up. So the network access layer combines layers 1 and 2, including the cable and the NIC. The internet layer is IP addresses and routing. And the transport layer is TCP and UDP. There are a few other layer 4 protocols, but almost those are the ones you hear most about. And then the application layer is everything above there, which is handling data after it has reached the right process on the right machine. This is a process of encapsulation. I thought this was very bizarre when I first learned it, and then I realized this is true of normal addresses too. If you address an envelope, it has the name of a person, a street address, a zip code, a city. It has multiple addresses at different layers of abstraction. It has a zip code, the general area, it has a street for the general area, it has a building, then it has an apartment number, then it has a human name, more and more detail of exactly what in the larger container I want to address. And that's what's happening here. So if you start with something at a high level like an email and you press the send button, it goes down through the layers. Layers down to 5 are probably in your email client doing things like encrypting it or compressing it or encoding the letters as ASCII, that sort of thing. Then you get down to layer 4. Here you make segments because your network cannot transmit a large object as one chunk. It has a maximum transmission data unit, and now there used to be a variety of different types of networks, but now everything is pretty much Ethernet, so that size is about 1,500 bytes for everything, which is horrible. It means when you watch a movie on Netflix and 10 gigabytes of data come to you, it moves them 1.5 kilobytes at a time, and every single one of them is independently addressed by all the routers in between, as if there weren't a million more following right behind it like ants in a row. That size has not changed, even though networks are now 1,000 times faster than when it was designed. Logically, it should be much larger, but progress towards all that is not happening. Anyway, so layer 4 breaks it into segments of whatever size you can transmit, which these days is 1.5 kilobytes. Then it's encapsulated and attached, given a TCP header, which tells it what order it should be reassembled in. Then it goes down to layer 3 and put in an IP packet and addressed with the IP address of the destination device so it can be found. Then it goes down to layer 2, encapsulated in a frame and now addressed with a MAC address to find the local area network device you're getting to. And then it goes off. Well, sent over the wire layer 1 as bits. So it's like you have 3 layers of envelope. You have an envelope, then you have a bigger envelope around it, then you put it in a box. Multiple layers of encapsulation. So the protocol data units are bits at the bottom, then frames, packets, and segments. They call this decapsulation when you receive something at the other end and now you strip off all the addresses, like throwing away the packing material, reassemble it, and send it back up the stack so it can now be presented to the user as, say, a movie. They can see, and they are no longer aware that this thing was assembled out of millions of little packets that were put together by your operating system.
I found a good mnemonic to remember, the
Yeah.
DSPFB.
Yeah.
Don't stop pouring free beer.
Don't stop pouring free beer. Okay, well, that's good. Yeah.
Remember.
That's a good one. Yeah. So, all right. So the MAC addresses are a unique hardware address, 48 bits long. The first half of it is assigned to the organization by, I think, the IEEE essentially. And then we're only supposed to vary the last 24 bits to specify all their devices. There are IP version 6 addresses that are constructed from the MAC address, and people are worried about the privacy implication of that, so there was a privacy extension to IP version 6 that replaced them with random numbers, so you wouldn't be telling everybody you connect to exactly who you are, so they can prosecute you for downloading copyrighted music and other privacy issues. So IPv4 is what we're mostly using, although not universally at all. I think we're up to something like 15 or 20% of all the traffic now being IPv6. But IPv4 is the old system with 32-bit addresses, which are written, unfortunately, as 4 base 10 numbers. So everybody has to learn to convert base 10 into binary, and generations of people suffer over that. So this is the famous IPv4 header right from the RFC. Everything about networking is defined by the requests for comment, which come through IEEE committees, and they become the standards, which, if you obey them, will make things interoperate. In fact, nobody really obeys them. Different people have different philosophies about how closely they obey them. They're sort of obeyed the way laws are obeyed, which means people mostly obey them, but they often cheat and cut corners and don't really do exactly what it says. And, not infrequently, the actual standards are defective, and obeying them will lead to a disaster. So nothing is perfect at any level in the system, but as far as it goes, those are the rules. So this is the header, 32 bits across, and a variety of 32-bit words here. So you have source and destination addresses that are 32 bits long. You have a time to live, a protocol, and other things here. The version number is always 4 in this case, because that's IP version 4. IP version 6 has a different header that, of course, starts with 6. IP version 4 has a variety of horrible things, and one of the most horrible things from a viewpoint of security is fragmentation. This is because there was a time in the ancient past when there existed this thing called token ring that could actually move 10 kilobytes in a packet, in a frame, at layer 2, and you could have a token ring network that then connected to an Ethernet network. So you send something from one IP address to another, and halfway through it has to be broken up into like 6 smaller frames from the original frame. And rather than just not delivering it and telling the sender to break it up into smaller chunks, the routers were able to take one big packet, cut it up into small packets, and send it as small packets. So they have a second breaking of it up, a second labeling, and a second reassembling. And this kind of repeats what should have happened at layer 4 with another layer where it doesn't have the controls at layer 4. And this turned out to be a really bad idea, and it made it possible to sneak malware through things by just breaking it up into a lot of little chunks. And this is what FragRouter does, a Linux tool that will break anything you want to send into 8-byte packets that go through 8 bytes at a time, pretending that I'm somehow a network that can only move 8 bytes at a time. So all the intermediate devices, like your intrusion detection system, can only see 8 bytes of the data at a time and can't really tell if it's a virus or anything. You can turn on the don't fragment bit, which will prevent this from happening. As far as I know, fragmentation has no actual value in a modern network. It's just sort of a security disaster, and it was removed from IP version 6. They threw it away. They just said, forget it. You'll never do this. If somehow you do reach a network that cannot forward a frame, it will just throw it away and send a message back to the sender and say, all right, send it in smaller chunks. Don't bother trying to cut it up halfway through. The IPv6 header is much simpler. They removed a lot of unnecessary fouled up parts of IPv4, but it's bigger just because the addresses are bigger, but it has less pieces. It also has this awesome thing called a flow label, which would make the internet 100 times more efficient if it was implemented, where you do not route the packets one by one, you just give them a flow, like the very first frame of your movie from Netflix defines a flow number at all the routers in between, and every future packet just follows the first one like ants without having to do any more calculations. That makes so much sense, but it's not happening at all. There's a bunch of advocates trying to get people to switch to it and not getting anywhere as far as I can tell, claiming that routers would be 100 times more efficient if we just did this flow routing. The protocol has the option, but it is not implemented by any common hardware right now. So you have IP addresses here, your MAC address is here, 6 bytes. It's 2 hexadecimal characters to make a byte. Each one of them is 4 bits. These things are called nibbles, the A and the C. Here you have an IPv6 address, which is 128 bits long, so it is 8 fields, each one of them containing 32 bits. No, each one containing 16 bits. And this colon means a bunch of zeros have been skipped. And then you have IP version 4 here, which is more familiar. So you can see them all there.
So
Yeah.
that's an example of your ifconfig. So you have both an IPv6 and an IPv4 address?
Yes, and not only that, everybody has an IPv6. This is a automatically configured link local address, FE80. Every interface, as soon as it comes up, has an FE80 address. If you're actually connected to an IPv6 enabled network, you will have another IP version 6 address starting with 2 or 3. And IP version 6, in addition to its many mind-bending features, is multi-homing. Almost every device has multiple public addresses, which is nuts. That's something we used to only do on servers. So in IPv6 you have several addresses. Yeah, but that's normal. You'd have both v6 and v4, and you can receive data over either one of them, which makes it a drag to try to monitor networks. There's a thing called multipath TCP that does the same thing. To make your network faster, you might have 2 ISPs, like Comcast and AT&T, and you can use them both to download something. So some of the packets go here and some go there. So now if you're sniffing the network to see what's going on, you're not getting the whole stream any. It's faster and more fault tolerant, but it fouls up network monitoring. Yeah.
Is there any benefit to keeping it on if you know you're not using? I mean, really, if you're
No. In fact, the first step of IPv6 deployment is to turn it off if you're not using it, because if you aren't using it, there's a bunch of automatically configured stuff that makes it possible for people to do abuses like DOS attacks over it and downloading BitTorrent through it and everything. That's why the step 1 in IPv6 deployment is learning how to turn it off until you're ready to turn it on now that you're ready for it. Because typically your IDS and your firewall is not IPv6 compliant, so you can't control it. Your bandwidth throttling stuff is not compliant. So step 1 is to thoroughly get rid of it, because it automatically configures on every device. Because if you buy a laptop or a cell phone, you want to be able to connect to every network, and you want to be able to connect to a network 4 years from now when they're really using v6. So they're all designed to automatically connect to v6 when possible, even though you're probably not ready for that. So that they will be ready when your network upgrades. Yeah, anyway, so there's a lot of security challenges. Like I say, many people don't understand how v6 works. Many hardware and software components are not really v6 compliant. Even the ones that say they're v6 compliant are typically lying, because the people that built this stuff don't understand v6. I used to teach a v6 class. It's much more complicated than people think, and they typically add a couple of features imitating v4, call it v6 compliant, and it's not really obeying the rules properly. And so anyway, it turns out to cause you to lose control of your network traffic to allow people to use v6 until you prepare for it properly. So you can disable it. A lot of places, one thing you can do just in Windows properties, you can just turn it off right there. That'll stop this one Windows device from using v6 in your network protocols there, and you can block it at firewalls and such.
So here they don't use IP6?
We don't have it native at all. We never did
I
it.
saw on the configuration it says the 6 to 4 tunneling is. When I got the automatic IP6,
You might have the tunneling.
It tries to send it to tunnel through 6 to 4.
Yeah, and you can do that. You can have
Instead
6
of
go over 4, but the City College doesn't have v6 native.
Yeah.
We never implemented it. We talked about it years ago, but then the accreditation crisis happened and lots of things. So, like most companies, we haven't upgraded to v6 yet. I upgraded my servers to v6, and then the provider I was using quit providing it, and I switched to just go back to v4, because now I use Cloudflare, and Cloudflare proxies it to v6. So my servers you can retrieve my web pages over v6, but my servers are actually speaking only v4. But you don't need to know that. The proxy in front of them converts it to 6. My servers don't have a certificate. They don't speak HTTPS either, but you don't know that. You don't need to know that. The proxy in front of it puts on the HTTPS also. So this is the system. Originally, the internet had only one class. The first byte determined the network, and all the rest determined the specific device on the network. And that was because the original internet had 4 servers, and they never thought it would grow much beyond that. But they did, so they switched to this system with Classful networking, which got us from like 1981 up to 1993, where the first half of the addresses are Class A, half of what's left is Class B, half of what's left is Class C, and there's Class D and E that's almost never used. And so these, Class C, you have 3 bytes to determine the network, and 1 byte to determine the device on the network. So you have many networks for small networks that can only have up to 254 devices. So that's the game. After that, we switched to CIDR, which split the internet into 32 sizes. so we do not have to have such a coarse distribution. This is because we ran out of v4 addresses. It always has been. The original network could only handle about 100 networks. Before there were classes, they switched to classes, which got it up to about 2 million possible networks. They ran out of addresses again, so they switched to this one, which splits it into the maximum number of possible chunks. And that got us through until about 2012, when we had to just go to IPv6 because there was no way to stretch IPv4 anymore to handle the number of devices. So Class A is a bunch of networks that can have 16 million hosts on the same network because they have 24 bits to vary. Only a few people have those, like the people have been around forever, like IBM. Class B is /16. City College has one of them, where you have 2 bytes to determine the network and 2 bytes to determine the host. So you have 65,000 possible public addresses, which is completely insane. These days, we're only using 30 of them. There is no reason to have thousands of public addresses. You just use NAT. But this was designed before that. Then Class C is the typical one where you have these small networks. You can only have 254 hosts on each one because you only have 1 byte at the end to vary. And you can split it up different ways. Like here's the City College wireless network. It's a /20, so it is 16 Class Cs put together to make a network that can handle 4,000 devices on one network for the wireless network. And you can split it any way you want within powers of 2 with that / number. I think that should be 4096. Anyway, I'm not going to worry about it. All right, so there's private address ranges. Anything starting with 10 is restricted to private networks, 172.16 to 172.31, 192.168. These are private ranges. If you send any packets to the internet with these as destination addresses, it will just be discarded. No one's allowed to reserve them for any one network. Everyone can use them only on local networks. If you send anything to the internet, it has to have a real public address, just like a real public phone number is needed. You could have a Centrex number on your campus where you dial 4 digits and you get a local thing, but anything going on the public phone network has to have a real public address, public phone number. It's the same thing here. So those are reserved for private networks only, and there are not enough of them. Sprint, for example, with their cell phones, has used this entire space 16 times over. So there are 16 Sprint devices with the same IP address going through 2 layers of translation. That's why cell phone providers were one of the first people that went to IP version 6, because they had big networks and there were not enough addresses for them. So the new system has an essentially infinite number of addresses. So you'll never have to worry about running out of addresses anymore. But the addresses are all sort of long and ugly. All right, what layer uses segments? All right, that's layer 4. All right, which addresses are 32 bits long? Okay, that's IPv4 addresses. All right, what class is that address in? Class C, as a big number is the first byte. All right. And what addresses are 48 bits long? Those are MAC addresses. Good, I see a lot of right answers there. So we got Ron, a whole new set of people. John E.
Turn off the network.
NA.
Yeah.
All right, so like I said, almost nobody uses so many public addresses anymore. They use network address translation. So many devices all share one public address. The old technique, which we still use for some parts of this college, although I think we're finally getting away with it, was static NAT, where you have a private address, but you connect it to a public address one by one. Pool NAT is where you have a group of public addresses translated one by one to the same number of local addresses. Those are very rare and old anymore. Now you mostly use NAT with PAT, network address translation with port address translation, and that works like this. You have a router which goes out, and that has 2 NICs, one to go to the local network and one to go to the internet, and they have 2 addresses. So this local one has a default gateway that goes out the other NIC off to the internet, and a local address of 192.168.1.1, and all the rest of these use that as their default gateway. So they send their traffic to this machine, which then forwards it onto the internet. And the only rule is all these addresses have to be unique locally. So you have 101, 102, and 103. The subnet mask must be the same on every device, and the default gateway must point to this, and they all have to be on the same network. So if you have a subnet mask of 255.255.255.0, that means every address has to start 192.168.1. If you change anything in the number of bits that are ones in the subnet mask, you're on a different network. So if one of these guys was 192.168.2, it would be on a different network and unable to communicate with the LAN.
Is NAT with Pat the same as NAT Overload?
No, NAT Overload is something different. I forget what it is. Anybody remember what it is? Yeah. There is something called NAT Overload, but I forget what it is. All right, so ARP is what you see, a ton of ARP packets flying around every network, because when you have one of these devices down here and they try to go to the internet, they know they have to get to the gateway, 192.168.1.1, but you can't send any network by IP address on an Ethernet LAN. You have to address it by MAC address. So the first thing this computer has to do to get to the internet is find out what MAC address is on this device. And it does that with ARP. So it's kind of nuts, but it's trying to reach things by layer 3, and it can't get there without finding out layer 2. So it says, who has this IP address? Tell me by IP address. And this tells you that IP address is at this MAC address, and it builds an ARP table in RAM of memorizing the MAC addresses of nearby devices so it knows where to send things. So that's the game. There is a thing called reverse ARP, which turns MAC addresses into IP addresses, and it was used to add new machines to the network before DHCP. It was just a way of assigning them addresses when they get started. Again, not common anymore. If this client wants to get to the internet, they have to send an ARP request saying where is the router, and the router has to send an ARP reply. That's how it works. And that works fine under normal conditions. The problem is, like almost everything in networking, this was designed in a long ago innocent age like the 60s and 70s when nobody thought about hacking and security at all. So all this happens with no password, no encryption, no authentication. So you can totally lie and send false replies, and all the devices will fall for it because there's no way they can tell a genuine reply from a forged reply. So you have ARP poisoning. Your attacker just sends lies about who's the gateway, and now all the devices send their traffic to the attacker, who is now in the middle, instead of to the real router, because they have no way to tell that these are false ARP replies. And you can reroute traffic any way you want. You can do denial of service attacks at layer 2 by sending false ARP replies that cause the traffic to get thrown away, and there is no defense against any of this, practically. Dan Kaminsky said layer 2 is an undefendable layer. The only practical defense against this is to keep weird people off your local area network. This is why you lock the door and use a WPA security on your wireless router and keep the password secret. You try to keep attackers from getting on your LAN. That's the most common defense here.
Firewalls.
Firewall does nothing. Firewall doesn't stop layer 2 traffic. It can't. You have to answer ARPs or you can't send or receive anything. So that's why ARP scans are great. You can turn a firewall all the way up, it won't stop any ARP traffic. Because if it did, you'd lose all networking. Firewalls start at layer 3 and above. There are some defenses at layer 2. Microsoft calls them network access control is one form, and there's another thing Microsoft added to some of their stuff, but it's rarely used and not very effective. Layer 2 is just very hard to protect you. Like I said, the main defense is to just keep weirdos from getting too close to your server. So unicast traffic is the most common, unfortunately. One sender and one receiver. This means if 1 million people are watching the same movie on Netflix, each one of them gets their own separate stream of data from the Netflix server, so it sends 1 million series of packets being the whole movie. This turns out to be a better experience for the end user because they can pause their movie compared to broadcast TV, where you have to wait for a commercial, but it does mean a whole lot more work by the routers in between and the servers and everything. Multicast is one sender to several receivers, which in the early days people thought would be used for things like broadcast TV over the internet, but that was never used for that. The only thing it's used for is router updates for dynamic routing protocols and things like that that are a very tiny amount of traffic.
Can Hulu use that?
What's that?
Can Hulu use that? Because they broadcast what's on now.
In principle, they could, but I don't think it's actually implemented over the WAN. I don't think it's a practical option, because actually it's quite expensive to implement. You have to subscribe to multicast groups in the routers, and your routers and switches have to know about this. So it's used in IPv6, and it really is quite a burden on your devices. So I don't think anyone's ever implemented on a wide area network like the internet. The only thing they've implemented there is Anycast, which helps you survive DOS attacks. So broadcast traffic is where you send one packet to every device on the network. And so you can send to the local network as 255, 255, 255, 255. That will just send to every device you can reach. Or you can have a directed broadcast where you give the network address to the network and then you put ones in the rest of the address. Directed broadcasts are no longer allowed to travel over the internet because of the Smurf attack. This turned out to be a first packet amplification attack. It turned out to be too dangerous, and the solution was to change the protocols so internet routers will no longer forward directed broadcasts. You can only do local broadcasts. You can use the directed broadcast address if you're on that network, but you can't send it from off the network and have it go over the internet and then broadcast to every machine on the network. Promiscuous access. Your network interface card was designed to work on a hubbed network where many different packets would be sent to you that are not really for you to see. So the first thing your network interface card does is it checks the MAC address of all the incoming packets, and if you're getting you'll call them frames. If you're getting a frame and the MAC address does not match the MAC address of your card, it throws it away and does not pass it up for further inspection, because it's designed to work on a dumb network that is so stupid that it actually sends frames to your device that are not for you. But you can turn that off. Most NICs have the ability to do it. That's called promiscuous mode, where it passes all the packets up. There is no legitimate reason to use promiscuous mode. If anybody is doing that on your network, they're probably a hacker trying to see other people's traffic. And Microsoft has various ways of detecting this. There's different ways to do it. Your network intrusion detection system should be sniffing in promiscuous mode, but normal users should not be. If you have a switched network, it hardly matters because the frames pretty much only go to the right place. But if you have a wireless network, they go right to everybody again because you can't contain them. So you're back to the situation of a hub where in fact your wireless card gets a lot of frames that are not intended for you. So TCP is up here, is the TCP header, which would be carried by an IP header and an Ethernet frame. So the TCP has ports, a 16-bit destination and source number. It has 32-bit sequence and acknowledgement numbers that are used to reassemble the packets, and it has other things here like these SYN and ACK and FIN flags that are used to do the handshake and to indicate when transmissions are over and to send acknowledgements so you can tell whether things got there or not. That's the special thing about TCP. It is reliable. So there is a handshake before you send data, and there are acknowledgements for everything you send so you know that it really got there. And if it doesn't get there, it's automatically resent until it does get there. So the first 1024 ports are called well-known ports. That doesn't just mean they're famous. It means it's a technical term for saying that they are reserved for a special purpose that many people will share, and you are not allowed to write some new game or something and use those ports. That is not in accordance with the RFCs, which is not to say it's impossible or forbidden. It just means, you know, you'll be breaking the rules if you do that. And like I say, people do break the rules all the time, but I don't know anybody breaking them. So there's things running there like DHCP and DNS and FTP and HTTP. If you want to write something, put your ports up here. There used to be two categories of ports up there, but Microsoft completely ignored the rules and used them all indiscriminately until they pretty much created a mess and the discrimination vanished for all practical purposes. And those are ephemeral ports, which you use for your end of a temporary connection like a browser session, or you use for anything that's not terribly common like AOL Instant Messenger, and everything else is up there in the 5000s. So a socket is the combination of all four numbers. You have a local address and a local port, and a remote address and a remote port. So this looks like an SSH connection to port 22 on some server, and here's my local end with an arbitrary high-numbered port. This is an ephemeral port. They're supposed to be bigger than 49,000. This looks like a Mac or an Ubuntu machine, so it actually obeys the rules and uses the big numbers above 49,000 for these ephemeral connections that are not servers, so no one will ever have to type it in. It's just used for my end of a connection as a client. That's called a socket. Those four numbers together are a virtual cable, which means data can go from one device to the other and one process to the other as if they were sharing their own line. It's all as if they had their own direct connection. It's not segmented in any secure way, but it's traffic directed. So traffic can now go from one process to the other without getting mixed with anybody else's traffic unless somebody forges addresses or something. So your socket has a state, and you can be listening, or you can be listening on a port like this one is. The top one is listening on port 631 for a file sharing request over Linux. It's waiting for a SYN. When it gets a SYN, it sends a SYN ACK, and then the other end sends an ACK, and when that's over, you now have established a connection. That's a handshake complete. So your SYN and ACK are used for the handshake. The ACK is used to acknowledge data receipt of packets. Reset cancels a connection. FIN ends a connection because it finished and all the data is there. And those are the ones you see most often. There are a few more, like congestion window reduced and such, but those are almost never used. Don't matter that much. There's the handshake. This is how port scanning works. You got to know your handshake. SYN, SYN-ACK, ACK. UDP has none of this. UDP has no handshake, no acknowledgement. You send data, you get nothing back. You have no idea whether it got there or not. That's why scanning over UDP is almost useless, because you almost never get anything back. But it's used for things where you want fast delivery and you don't need perfection, like a security camera, where it's a live feed and you just can tune in and watch it. And if a couple of packets get lost, who cares? You don't want it going back and trying to fill them in later. Or live music, for example, where if there's static on the line, that's tough, but you certainly don't want it trying to fill in the music later. Just keep it coming. All right. It's very rarely used. I mean, it's used because almost the most common situation is you want to make sure things get there and you use TCP. UDP is used only in a few special cases. So what kind of transmission uses that address? All right, that's a broadcast. It's the undirected broadcast. All right, what ports require administrative privilege to listen on? Forgot to mention this. This will bring it up. The first 1024, you have to be root to listen on them, or administrator. That's to encourage you not to use them for frivolous stuff that you're writing, like games and things. You're supposed to use the high-numbered ports for that. All right, what flag initiates a connection? Okay, that's SYN for synchronize. All right, what UDP flag initiates a connection? There we go, I'm not fooling you people. There's no handshake, there's no connection. You just spit data out. All right, so we got one more section. I'm just gonna do it. Normally I'd take a break, but I'm gonna do it and then I'll get out of the way for the student presentations. And we'll take a 10-minute break and people can put their slides up here and such. But let's do one more section first of this stuff, which should be like a review and hopefully not too hard. So we have ICMP, used to send information about network conditions, like see if you can reach a server, tell you if a router had to throw away a packet for some reason, and so on. Ping requests a reply just to see if it's there. Traceroute sends a whole series of packets with low TTL numbers, so they will expire on the way to someplace and send back error messages, which are used to trace out the route that you're following to get somewhere. So that's how traceroute works. The packets with TTL of 1 only make one hop towards the destination and then die, and you get a time exceeded error coming back. The next one make 2 hops and die, 3 hops and die. So unless the route actually changes a lot, you'll get a nice trace. When I was designing Firewall Hero, something used for this competitions, I found out that in practice these routes change a lot. The number of hops to get something actually fluctuates from like 6 to 7 to 8, a lot, more than I thought. So Unix and Cisco send UDP packets, Microsoft sends ICMP packets. You can send any kind of packet with a low TTL to this purpose. It's arbitrary which one you use. Telnet was originally intended to connect a keyboard to a computer in the same room over twisted pair cable, and then ported to move over IP over the internet, so it sends your characters with no encryption, which is very dangerous. A lot of people continue to use it, but we should have abandoned it decades ago. SSH is the replacement, which encrypts your data and is much, much safer than Telnet. FTP is the same thing. It sends passwords and data unencrypted over the internet and should have been abandoned decades ago. It just was a way to share files over the internet. There's an active and passive FTP that use different ports. In addition to not encrypting anything, this passive FTP uses an arbitrary ephemeral port on the server. So FTP is a security risk because you have to configure your firewall to let anything through that claims to come from port 20, which is rude. It means you can sneak traffic in by pretending to be FTP traffic. It's hostile to firewalls. It was developed before firewalls existed and did not cooperate with the idea of having firewalls filter in by port number. TFTP is even dumber. Uses UDP on port 69. There's no authentication at all. It's used to upload firmware into routers and IP phones. And if you run a malicious TFTP server, you can dump malicious firmware into devices. It has no password control at all, and pretty harsh. And one of the early versions of it actually had a serious vulnerability in the RFC. where it would lead to a denial of service condition if you actually obeyed the rules, which they took a while to be detected and fixed, the Sorcerer's Apprentice attack. So SSH was the secure replacement for Telnet. There was also a bunch of other things, rlogin and rshell, which were like Telnet. They would connect from one server to another without any encryption, and there's SSH replaced them all. It also used SFTP and SCP, which moves file transfers over SSH, so they're encrypted and much safer. And you can tunnel anything through port 22. SSH, their old version was old and vulnerable. SSH v2 is the current. SNMP is used to send email on port 25. It is not encrypted, and the passwords are not encrypted either. So it's also being upgraded to a secure one, secure email very gradually, using HTTPS for hop from hop to the devices. POP was used to download into your local client like Eudora or Outlook, and so is IMAP. Those things are still used at companies, although almost nobody at home uses them anymore. Everybody uses webmail these days, where you don't actually put your email on your device, you just view it on the server. But if you want to run Outlook, then you actually store your email on the client. This was popular to keep email off the server because the servers couldn't afford a big enough hard disk, but all that is pretty much over. DNS uses UDP, no authentication, no encryption, so every domain you go to is sent in plain text over your LAN and over the internet to a resolver if you use a remote resolver, so it is quite a privacy risk. This is very easy for administrators to catch people who are doing inappropriate things on the internet. You can just look for the domain names and you will have the source address and the time when they went there. You can totally see who's doing whatever you're not allowed to do at your company. So it is handy for network administrators, but not very good for security. By the way, it's also easy to spoof DNS, just like ARP, because there's no password, no encryption. You can send false DNS data, and everybody will just fall for it because they have no way to tell the authenticate packets. That's what DNSSEC is supposed to fix, but it only fixes an esoteric problem at the server. It doesn't fix any problems at the client. It doesn't fix the privacy issue or the authentication issue for the client. It just prevents these servers from being fooled by forged addresses from other servers. So it doesn't really solve a whole lot of DNS problems, and it turns out to be quite expensive to implement, so it has been very slow to roll out. Most companies just see it, even more than IPv6, as a whole bunch of work for no apparent benefit. So very slowly it is rolling out, but in practice it's not doing anybody any good yet. Once it's all the way out there, some attacks will no longer be possible. It doesn't offer a lot of value for all the effort for most people. So there's online Digg services you can use to bypass filtering because most people don't implement the advanced DNS stuff on their network. If you use an online service to get unfiltered DNS, you can then do a Digg for IETF.org and you will see these long cryptographic signatures. That's DNSSEC. These long signatures will prevent the DNS servers from being fooled by a forged record. And if everybody enforced them, they would actually protect your client. But nobody does that because most people aren't signing their stuff anyway. So if you block the unsigned stuff, the internet would go dark. So it's the kind of thing that isn't going to help until pretty much everybody uses it. And nobody wants to bother using it because it offers them no benefit in the short run, so you have a chicken and the egg problem, and it's not growing very fast. SNMP is the protocol used to control your network devices over the network. It uses UDP port 161. SNMP version 1 and 2 send these passwords called community strings in plain text over your network, so they're very insecure. There's a version 3 that has encryption and is much better, but almost everybody still continues to use version 2 because until you upgrade all your old hardware, you have to use version 2. So in fact, there's a whole lot of these unencrypted things. This is why there was a talk at Hope a few years ago where this guy was checking police radio encrypted traffic to see if he could decrypt it. And he said if you got a book on practical encryption, the first chapter says, first check for plain text. A whole lot of stuff that should be encrypted is in fact not encrypted, and that's the case. If you just sniff networks, there's a lot of people using unencrypted protocols, even when they ought to know better, for various reasons. HTTP, for example, sends data over the internet and people are logging in. It also has no encryption, so you don't know who you're talking to and everybody can read all your traffic, which is kind of nuts. So the internet is rapidly moving to HTTPS, where everything's encrypted with HTTPS and certificate authorities. It's a lot better than HTTP, although nothing is perfect. BootP is a really old protocol that was before DHCP. It was a way to distribute addresses on a LAN when things boot up. DHCP is the modern protocol used by almost everybody. When you boot up your device, it sends a DNS DHCP request saying, help, I need an IP address. Will somebody give me one? somebody gives you one and you obey it. Again, there's no encryption, no authentication, but it works in most, yeah.
You know, on Wireshark to find DHCP, you got to type in boot P.
Yeah, I didn't know that. I always had to type in UDP.
Yeah.
That's good to know.
Yeah.
Anyway, all right. Yeah, well, Wireshark is really a community effort, so it's probably, Wireshark is probably so old, it probably dates from the time of boot P,
Yeah.
the old Ethereal, its old name. There was a massive DHCP vulnerability. Like a buffer overflow in DHCP a few years back. That was pretty awesome. These really old protocols, people use them for decades, like NTP had a major flaw. Just a lot of these protocols have been sitting there, nobody's looked at them in 15 years. Then when somebody looks, they've got some huge problem. Like about 5 years ago, they found out that all the cloud servers could be taken right over through the floppy driver. All those virtual machines had virtual floppies that nobody even remembered existed, and the virtual floppy driver, of course, had all these vulnerabilities nobody ever looked at. This kind of stuff keeps happening, you know. Whatever part is boring and old is probably has not had any updates in 10 years. Anyway. Okay, which utility sends a series of packets with different TTLs? Okay, that's traceroute. Good. All right, which one performs file transfers with no password at all? Okay, that's TFTP, Trivial File Transfer Protocol. Which protocol is on port 22? That's SSH. All right, and which protocol has RR SIG records? All right, that's DNSSEC, Resource Record Signatures. Okay, so password is here, okay. Then Ron is ×3, and Devin, right, is a winner.
So my name is Mark Singh, and I've been a student here for 3 years or so. I've taken most of Sam's classes, and I'm going to talk about Digg and DNSSEC. So Digg is a nice tool for resolving names to IP addresses, and some other tools you might use are ping or host or NSLOOKUP maybe, but they don't quite give as much info out as Digg. One of the nice things about Digg is this is what the DNS packet, the RFC looks like for it. So the Digg's default output is really similar, so it's kind of nice to have that. And this is the IPv6 output. So as Sam said before, it's usually transmitted over UDP and TCP if it exceeds the UDP limit. But TCP introduces latency with the three-way handshake. So one of the new things is the eDNS. This is a new part of the new RFC for DNS. So that stands for Extension Mechanisms for DNS. And as you can see, the UD packet size can be increased. Some companies, this company in particular, the Ultra DNS, has it to almost 64K, which is the packet limit size. But as you can see, we're only still using 188 bytes. So it doesn't pad it at all, but they just negotiated a size that they can use up to that limit, which will come into play when DNSSEC comes out more and the packets get bigger. This is what DNSSEC looks like. So you have, as we know from our reading, it's a public key to digitally signed signatures for DNS responses. So how does that work? Well, for PayPal, this is the chain of authority. So if we're looking at PayPal, they go to the comm servers, which ask the root servers down the chain for information. For DNSSEC, we can ask the root servers what is your digital signing key? And we see here it's a DS30909. If we go back and ask the comm server what they need a DNS key, we see that the root server signature down there. And so we've established a chain of authority from root to the comm servers. And then we can go and ask the comm servers, well, what's your DNS signing key? And they're 21037. And we can go back and ask comm server and ask for PayPal's record, and we see that that's also signed too. So that the chain of authorities or chain of security has gone all the way down from the root servers and made it down, and you can tell that this is a complete record. So I had more Digg stuff, but I didn't know if I'd be able to fit it in, so I didn't put it in the slides. So that's. There's Digg has some really cool commands that you can put in that, maybe another talk.
This is me. This is some of the certificates that I have. You see that I do not have CISSP. Some of them I missed, I think about 4 or 5, including A+, Security Plus, and some other from Linux work. Anyways. So this is me, and I have worked for different companies here in the United States during the last 5 years. Now I am a PCI program manager at Sephora. And one of the things in the security team, if you work for a company, they come to you for any new contract and ask you, hey, we have a new contract with this vendor. Please review the contract and give us a green light for the security. And you keep saying that, hey, I'm an engineer, I cannot do that for you. I'm not good at, reading these thick contracts. And they said, oh no, you are the only security person here, or your team, and you have to do that. And one of the things that I see in almost 90% of the contracts is this statement. What? Okay. It means that almost nobody in the companies that I worked for, you saw those things, those are very famous companies, knows about open source, freeware, shareware, or free software. They may know a little. So I'm an open source user for last 20 years. So I wanted to share some very basic information about open source software. And okay, is open source software same as free software? I do not care about shareware or freeware. Those two terms doesn't have a kind of terminology in the IT world. But free software has terminology. Free software has a kind of terminology from Free Software Foundation, and open source has from OSI, not OSI that we learned today. So open source initiative, yeah. So, and you can say that open source software is free software. Technically, they're not the same, but it's very, very hard to find a software that is open source but not free software, or vice versa, based on the definition they provide. So this is the kind of philosophy behind that. And that free software, it's not about cost. It's about free as in freedom. So, wow, I put 2? Anyways. And this is not about this. This is about the source as well. This is not only about the cost. Cost is not important thing here. So this is not about the source. This is about the license. And what did they put in the license? This is an iTunes license that says that, oh, you cannot use this software for illegal whatever in the United States. even if iTunes provide the source code, even if it is free, when they put such a thing, it's not free software. It's not open source. So Free Software Foundation provides for freedom. They say that, okay, go through the license, read the license. If that license guaranteed these 4 freedoms.
1 minute, 1 minute.
Oh, sorry, go ahead. Sorry, I will go ahead. And if it provides these 4 freedoms, it is free software. And open source has 10, but they are almost the same. So you start from 0, it's computer, and freedom to run the program as you wish for any purpose, not like the iTunes. The freedom to study how the program works, so it means that you need the source code. The freedom to redistribute copies of the one that you get, and the freedom to redistribute the copies of the modified software that you modified.
Okay, got it.
That's
Stop
it.
there. Thank you.
Thank you.
I'm calling this top 5 footholds. I should say my top 5 footholds. This is just what I've seen in pen tests and what usually works. None of this is really technical. None of this is really hard. It's usually like low-hanging fruit that escalates into something more. That's why I say what happens before the pivot. Basically, you just want to get a foothold, and then you want to move around. That's all the pen test works, and usually you get some low-level user, and you just keep on circling and circling until you get something better. A little bit about me. That's my name, Devin Ertel. I've been doing security a pretty long time. I probably did every role you can possibly think of. Almost every industry I've probably pretty much been in. And it's mainly been offensive, though. So most of my career is offensive. So yeah, I'll get into it. So first, I just kind of wanted to get into this. I don't know if anyone has seen this before. It's called the attacker lifecycle. Funny enough, like I worked at an IR company. I'd never even heard of this, and I was doing pen testing for a long time. And I was like, yeah, that is exactly what I do. So I actually learned about it from people doing IR. But this is exactly what happens, right? Initial recon, initial compromise, foothold is what we're going to talk about here, my 5 favorite ones. And you want to escalate privileges, more recon after you get those privileges, see what else is out there for more access, move laterally, move around the network, maintain presence, so you always want to keep that like hook in, so you don't want to just lose it. If a virus scan is going to pop you or find you, or someone's going to see some of your channel that you have back. And then finally, you'll get some user or some piece of data where you call it a win, and you just walk off. We used to actually ring a bell every time we hit it. So first one, this is all you guys are like, this is all super easy stuff, right? So default and weak credentials. Usually what I would always find is Tomcat, JBoss, WebSphere, Jenkins. Everyone would try to attack like a sales network or something. In that part, I always went after the engineers. They usually have admin access. They're going to be installing stuff. They're going to be forgetting about stuff. So they usually will have a test JBoss server sitting up, default creds or something easy, right? Like the first thing I'm going to do is try password on it, right? I don't even try. I just manually do it really quick. And then once you get it, you basically deploy like a web shell, and then you're getting commands on the system. Hopefully that's running with a little bit of privilege. If it's not, it makes it a little harder. But anyways, at least you're getting something, some user, and then again, we just kind of keep pivoting around. Next one, insecure printers. Some people ask, well, what the hell? Why do you care about printers? I love seeing printers. Usually they're going to be hooked up to like AD or some LDAP server. When I say insecure printers, they're like they basically have the admin interface wide open, so you just log into it and you just point that printer. You open like a listener, like a netcat listener, right? And you just point your listener to your box, and then those creds come to you. So then all of a sudden now you got like, what you want is like AD credential, right? That's the funnest stuff. It's just popping around AD because you can really pivot. Power Empire, Shell Empire, whatever, I forget what it's called right now, but that's what everyone's using right now. So you usually will get domain admin off a little insecure printer, which is, never would guess that. So I put this in here just because it's kind of cheating, unless like the customer actually wants it or you're in a full-on red team engagement, but it's obviously nets people all the time. phone or email. I always say email is a lot easier. You can pump out a whole bunch. This is pretty much my favorite scenario. Find a company's VPN site, mimic that page, register a domain, add secure in place or something like so it's secure-company. Or if it has L in there, I love doing it like if it has I, you do it like an L. You can kind of like trick the domain out a little bit. So you register that domain, put that VPN site on there, find their security person on LinkedIn, send out an email from them, and then you can basically say, we're upgrading our security, put your credentials in, and you'll probably get them. Next one, unpatched systems, obviously. This is pretty easy. You can find this via Nessus, like a quick scan that's super loud. You can do it manually by fingerprinting. This is my favorite, MS-0867. I popped a lot of boxes. Everybody did, and it's probably still around. And that's why someone actually made a birthday cake about it. It's such a reliable exploit. Yeah, I think that's it. I'm gonna have a minute. So, dumpster. So yeah, open shares, NFS. Could be NetBio or Windows shares, and you're looking for passwords, shell scripts, batch files are always there with the username and password in there, or sensitive data. So, because if you can't find anything, at least you found some sensitive data that you can bring to the customer. And then that's it. So, anyone had questions? Did I make 5 minutes?
Okay, everybody knows the blockchain was introduced by Nakamoto, and then a year later, that's when the Bitcoin came out. How do we get rid of this top part? A blockchain, one thing I didn't realize, blockchain is decentralized distribution electronic ledger. And so it's like a bunch of blocks are arranged in chronological, and they're all added up to the blockchain. And the blockchain is decentralized, like the second diagram there. Each node of the network downloads a copy of the chain, and everybody has to agree on the chain. There are two types. Transactions are actions created by the participants, and the blocks are the recorded transactions. And how does it work? The blockchain is public, so every participant can see all the blocks stored in them, but they can't see the actual information because everybody's got their own key to secure it. And it removes the central dependencies so that it has less chance of getting hacked if it's spread out across different nodes. It's supposed to be faster than the normal transactions, and economic is supposed to be cheaper, more secure, and more transparent. Secure, all the blockchains have hash functions with timestamps, can't be changed. Tamper-proof, decentralized feature, blockchain, increased popularity. The original function of Bitcoin digital transactions. Many cutting-edge financial firms are supposed to be starting to use it. Also, there's a compliance, KYC, know your customers, and anti-money laundering was supposed to help this. The blockchain is supposed to help this. Some of the technologies. One of the things I noticed, it was talked about DNS can be validated because all the different nodes have to agree on that the blockchain has the valid ID. That way it can't be forged. And IoT devices, they have if they're on the network and they have any security, then they're connected together by peer-to-peer. Then they use the blockchain to make sure that it's that they're secure. And making passwords obsolete. The blockchain can authenticate users, doesn't need the password. There's one where that they could also validate the doctors for medical information, so you can tell if your doctor's legit or not, license. Smart contracts is where you buy a house and stuff. You can transfer contracts back and forth without actually having anybody to worry about forgeries. And to learn more about blockchain, take Sam's class.
All right, good evening, everybody. My name is Michael LeMay, and I'll be talking about firewalls. Pretty sure everyone knows exactly what a firewall is. You have them on your computer, and do they work? Yeah, I guess they do. Depends on what you really use. So what is a firewall? So a firewall is a network security system designed to prevent unauthorized access to or from a private network. Firewalls can be implemented via a software or hardware, and they're frequently used to prevent unauthorized access from the internet to the intranet. And all messages entering or leaving the internet pass through the firewall, which examines each message and blocks those that do not meet the specified security criteria. So types of firewalls. Proxy firewall. It's I guess what I have up here is pretty much an earlier type of device. So it serves as a gateway from one network to another. It's actually not on your a proxy firewall you are going to connect to. It's going to be not necessarily on your firewall, something you connect to, and then it's much slower for that reason because you're proxying into it. So it's whatever you're hitting from the internet is hitting that first and then coming back to you. So I think it's a really good way to firewall to use, but you'll see that there's firewalls that actually have implemented this into it. And another one is stateful inspection firewall. This is actually a traditional firewall. And I believe Windows Defender uses this. And it basically monitors all activity from opening of a connection until it closes. It's state-based, so it's going to use ports and whatever the state that you put it in, whatever you decide to make for that that protocol. And these two I actually sort of kind of want to put together because unified threat management and next generation firewalls really have a lot to do with each other. And UTM device typically combines in a loosely coupled way the functions of a stateful inspection firewall with intrusion prevention and antivirus. It may also include additional services and often cloud management. UTM's focus on simplicity and ease of use. And which goes right into next generation firewalls. And at our school, I believe we have Palo Alto networks, which you can see if you're taking a lot of SAMS classes, we have to use the other internet that he has because VPNs are blocked via Palo Alto networks. So for our next generation firewalls, they're actually a layer 2 through 7, but like Sam was saying earlier, I guess layer 2 is not a layer that a firewall can actually operate on. So it's layer 3 through 7 actually, which goes all the way up to application layer. And it encompasses the proxy, traditional, and the UTM firewall. The major difference in the next generation firewall is it's capable of deep packet inspection. And what deep packet inspection is basically a form of packet filtering that isolates, identifies, classifies, reroutes, or blocks packets with specific data. Unlike conventional firewalls, which they examine the packet header. So the biggest alternative to the traditional firewall, they are the best alternative to a traditional firewall. They're more expensive since they encompass a wider range. And one thing I don't have on here, but I'm happy that Sam brought it up earlier, is that Palo Alto firewalls, since they are hosting a class, it's probably one of the things you probably want to go to, since the firewall class here is usually just talking about,
1 minute.
I want to say it's pretty old, so it talks a lot about traditional firewalls. So that's a class that actually is there any veterans in the classroom at all? There's besides the one that Sam's doing, or the one that Sam put up, that's for everyone, but there's also another Palo Alto class for veterans, which is actually right after spring break, and you'll get an ACE certification, which I'm not sure if the one that is being offered at Foothill is going to have that certification. So I would recommend that to any veteran in the classroom, and the other one for anyone else who can't. And if you want any more information on that, since I've already taken the class of Palo Alto networks, you just hit me up and let me know, and I can get the information to you.
Cool. That's it. Thank you. All right.
Excuse me, so do we have Palo Alto networks here?
We don't have the class, but we have
Devices here.
We don't have devices. have OS. You can put in a virtual machine.
No, I'm talking about the CCSF. Does CCSF use?
We have Palo Alto protecting the network here.
I remember that last semester in your 1, 2, 3 class.
Yeah.
So you asked us to use VPN over port 53.
Yeah.
So if the Palo Alto next generation is enabled there, so it shouldn't allow us to do that.
The Palo Alto has the ability to block it, but apparently they have not turned it on here.
Okay.
Yeah, that's right. Because yeah, the network here is pretty easy to sneak out of, which is not a limitation of the Palo Alto, but it's the way they got it configured.
Okay.
Which you'll learn about if you take that course.
Yeah, they should take the course.
Hello everyone, my name is Anvin Paiteratel. I'm going to talking to you about activism through hacktivism. So as we all know, like there's a lot of U.S. policy going on around like hacking, and so I kind of want to just take a brief look at where we come from, and it's not a very technical presentation, so sit back and relax. All right, so American Policy by Pop Culture. Everyone remembers this movie probably. The earliest references to an individual hacker in a motion picture, surprisingly, was The Italian Job. And then afterwards was Tron, War Games, The Matrix, and Swordfish. Out of those 5, 3 are pretty possible, and 2 kind of put the world at notice of what are hackers their ability able to do. I'm speaking, of course, of War Games and kind of Swordfish. Tron, you can't really get too involved in, and Matrix, of course.
Stand yourself in.
Of course, if you haven't seen the movie War Games, I highly recommend it. A young hacker finds a back door into the military central computer, starting in World War III. It was a very popular movie, box office success. One of the main images from the movie was this quote that I found. The only winning move is not to play. And I thought it was kind of similar to a lot of our policy. And so we'll just kind of disregard it, see what happens. So thank you, Matthew Broderick. Hacktivism definition: the act of breaking into a computer or computer network for social political purposes. And so while I was going through it, I kind of came into ethics of hacktivism. And so there was 2 principles of ethics that I kind of sidetracked into, and that was a universality principle, which is an ethic declares an action right or wrong given a situation. It must also declare the action right or wrong given another situation, given similar circumstances. You can apply that wherever you want to deem reasonable. And then the justification principle: any ethical determination must be justified by appeal to a general moral position. And for those of us who are morally challenged, prejudice is not an acceptable emotion. If you're reacting because of something that's emotionally happened to you, that's not a moral justification for you. False facts, as well as appealing to others because you're bandwagoning, parroting, or being socially engineered. You got to be kind of it's kind of a double-edged sword. You want to be aware of what you're influencing and what's influencing you. So your words have power. And so then the ethics of these blurred lines, of course, there's consequences. And if you guys are a fan of John Oliver, the Late Show, I forget, or Daily Show, something like that, there's something called object permanence, which is if you leave your oven on at home, you can't go leave your house and expect the oven to just be off. There are consequences of you having turned that oven on. So that's what object permanence is. Deontology is the nature of duty and obligation. So in our society, there are roles that everyone plays: police officers, students, teachers, everyone. So is it, as activists, is it the role of duty? Is it your role to be on the forefront and hacking, to present your opinions and your policies, or in nature, is it the duty of the law enforcement and their obligation to prevent you from doing such? And so that's where it kind of becomes blurred lines, because a lot of hacktivism will be classified under civil disobedience because it's nonviolent. It's your right to freedom of expression, right? So basically, when I was going through the history of all this, I kind of found activism. There's WikiLeaks, Anonymous. You got to be aware of there's always the possibility of lone wolves, the swarm hacktivists. It's not always open or democratic. An example was in 2011, we saw Occupy Wall Street, and that was actually an international thing. So, and I kind of related it to the printing press, because the printing press really changed how society looked at the world and how the era of mass communication really sculpted society. Quick question: percentage of the world population enjoying free press, which is coverage of political news, journalism is safe, state intrusion in media affairs is minimal, and the press is not subject to heavy obligations or economic pressures. 13%.
We're going to have to stop it there. Thank you.
Thank you.
I'm Danny, and I didn't want to make a PowerPoint, so I made a hacking demonstration instead. Does the audio work, Sam? Does the audio work?
It doesn't amplify in the room, but it should. Did you wear the thing?
No, I meant for the
recording.
For the recording.
Oh, I have no idea.
You want to play it?
I have no idea. Try and see.
This is a hack the box demonstration, and we are hacking the box nibbles on 10.10.10.75. So let's get started. So I have Armitage open here, and we're going to do a quick Nmap scan of all the ports on the host. We will see that port 22 and port 80 is open, meaning a web server is running on the machine. So we're going to switch to our browser here, and we're going to type in the IP address. And we will get a simple web page that says "Hello World." Nothing else seems to be on the page, so let's take a look at the source code. In the source code, we'll find that a nibble block directory exists. So we'll just copy nibble block and type it in our web address. We will get this ugly looking blog that doesn't seem to work at all. You can dir bust the whole thing and get these useless links, but Google is your best friend, so I use that instead. So I looked up nibble blog, and it brings me to a demo site. This demo site shows me that there's an admin.php. So we go back to our host and we plug in admin.php, and it brings us to this login page. But now I was stuck. Looking through all the directories did not give me any credentials, and the default passwords did not work. The system also blocks you after failing 3 times. But I noticed something. I noticed that in Hack the Box, the creator incorporates the name of the box as a hint. So after a few dozen guesses, I tried admin as the username and nibbles as the password. And voila, we have logged in. We can see other people and their failed login attempts, but we don't really care about that. We only care about exploiting it. So we'll just do another Google search for nibble block exploits. Unfortunately, we get an exploit that is already in the Metasploit framework. So we'll switch back into Armitage, and we see that our scan is complete, and we'll look up nibble block in the exploit section. Double clicking it will give us a description saying that we can execute arbitrary PHP code by uploading a file. So we'll quickly fill in the information of our machine, our IP, the password, the target URI, and the username. And make sure we're using a reverse shell connection. So launching the exploit, we'll see that we get a interpreter session, and we'll also see that the machine is now compromised. So we're going to launch a quick command shell and do a ls command and do pwd, who am I, and then we'll go to root, then we'll go to home, and then we go to the user, which is nibbler, and we will find user.txt. So we'll just cat the file and we get the user hash. To get root, I use a script called linenum.sh, which is a Linux enumerator, and it checks a bunch of files for privileges and possible system vulnerability. So we found this section where it says that the user nibbler may run sudo on monitor.sh without a password. So we'll go back to our console here, and we can see that monitor.sh has read, write, and execute privileges. So we'll just replace the contents of the file with echo sudo cat and the location of the root.txt file. And then we'll run the file with sudo. But it also seems that it'll time you out for no reason at all. So we'll try it one more time. And we get the root user's hash. So what do we learn? 1. Don't use common passwords. 2. Linenum is a great enumeration tool. And 3. Google is your best friend. Thanks for watching.
Hi everyone, my name is David Andres Sangiano. I'm an IT specialist in freelancing, and I'm starting to learn more about security in general. So I want to talk to you about cybersecurity conferences of this year. Agenda, obviously, where should I go, how much it would cost me, when and where are they. We'll talk about RSA, some of the stuff that's there, and we'll also talk about RSA Conference College Day, which a classmate pointed out to me, and talk about that. So, why should I go? It's all about networking. It's about relationships, sharing information, and knowledge, and strengthens the community as a whole. You don't need to be a cybersecurity expert to attend as long as you're willing to learn. If you don't know anybody, you're guaranteed to make new friends before you leave. All you have to do is just say hello. Security education. Most security certifications require some kind of continuing education, and conferences can often cover that security education requirement for the year. Community outreach. This community is based on mentorships, which often format conferences and networking events. All conferences offer opportunities to be mentored or become a mentor, sometimes both. Smaller cons provide attendees with a better chance to interact with speakers, while larger offer opportunities to meet mentors within the crowd. How much it would cost me? Conferences. There are conferences for all budgets and experience levels. RSA, for example, costs a few $1,000s if you're going for a full, the full week. Combined with certification training, the tutorial that they provide there, airfare, lodging, food, it can add up. Besides SF is a Million Small Money Conference. I believe this year for a ticket, it's like $50 for a ticket. There are volunteers, so you can actually volunteer at B-Sides and get a free ticket for a day after. There are other cons. DerbyCon is the largest security conference in the southern United States. TorCon, ShmooCon are incredible conferences, I believe, that are on the East Coast, I believe. CANSET and West is a Canadian security conference, and Sector is another one. So when and where are they? So here are a list of a few cons and their dates and where they are. Mostly I tried to find ones that are just in California in general, but there are like DEF CON 26 is at Las Vegas, Smooth is at Washington, D.C., the RSA conference is here in San Francisco at the Moscone Center. B-Sides is also at the Metron, which is right next door. So there's that. So why would you attend? As InfoSec professionals, we are always learning new things, new technologies come out. They also offer CLE or CPE credits for the IAPP, the ISACA, ISC squared, which provides this certification, the CISSP, which will cover that, and the GIAC. So here are on the right-hand side are a couple of agenda tracks that they offer at RSA. You know, some of them are live demos that they do, like the SANS tutorial. A couple of learning labs that they do over there. There is the DevSecOps, which actually offers a live hack of a kill chain. And then they offer special events at RSA. For our RSA Conference College Day, there is a promo code which gives you a free ticket on Thursday, and it's right there, and there are some things that you have to remember to include when you sign up for that. So, thank you, and Formy would like to say thank you.
I don't know who was first. I heard Student Day. I noticed, or not. They have more than the Student Day. They have a Student Pass this year, and the workshops are available to the Student Passes too.
Yes.
I was looking at the workshops. You can do the.
Yeah.
So you can sign up for the different ones?
Yeah, but so the actual Student Day is you have to have 12 units. You have to be enrolled in 12 units.
Oh.
Yes. So whereas the College Day, you just have to show that you either are enrolled in a class or have to have graduated in 2017.
Okay. Wait, which one was that? The day is the.
The day is just you just have to show proof of your
pass. You have to be 12 units.
Yes, correct.
Thank you, Craig.
Yeah.
Besides, it's $25 for the student discount.
Oh, okay.
Yeah, so you have to email the. There's an address.
Yeah, I tried to look. I tried to look for.
It's on the website. Just send the email to and it'll give you like a.
Well, I just decided to volunteer because
they pinged for more volunteers right now. There's still like half the slots open for volunteers, but they're gonna fill up fast.
Yeah,
everybody's pushing it.
Yeah, I just decided to volunteer because I had nothing to do, so I'd rather just do that.
Do we just email for the volunteer positions again? The same place, or?
It's actually on the website, so you can just go to B-Side's website and click volunteer.
Okay.
Yeah.
And you pick your shifts.
Oh yeah, like I'm doing check-in in the morning.
Yeah.
Don't forget you have to do 2 shifts.
Yes.
8 hours.
So are there any more people who want to give talks? Do you?
I could give an update. If that works. I don't have my slides or anything, but been working on the server stuff.
Woo.
Good.
If we got time.
5 minutes.
All right. 5 whole minutes. We were watching them over there, so let's see. I'm nice and sweaty. Is this still going out? We're watching the stream. I don't know if the stream's still going. I don't know if I want
college
the stream
stream
still
is
going.
going.
It is. Oh, right. The Zoom stream is what we were watching. So while I bang on the mic here for everybody. Yeah, maybe I can try and give a live demo here on the machine. No, it's all over VPN now. Yeah. So, we got, so we've been working on the server stuff. Server Club started last Monday. We had a really good turnout. I think the Monday before as well. No, it was last Monday, a good turnout for the Server Club. And got a lot of stuff. We went over all the equipment in the racks, which is what my slides were going to show a little bit of pictures of. Some of the CPUs and everything, just going through how all the servers operate. We got the ESXIs all running during the club, and then this week on the club we were talking about doing a key exchange for the VPNs. We'll have to actually hand those out some way securely, and we're looking for suggestions. We're going to be running the VPN for everybody, and I think the bandwidth's there to handle everything and give everybody access, different levels of access, what can apply, I guess. Our group is coming together. I'm going to be been appointing some communications officers to help me maintain that. That'll help with also the user relations, I suppose, which will be everybody that's not actively managing the servers, but wants to use them, and we'll get access to virtual machines, attack infrastructure, defense infrastructure, and during the setup, everybody's welcome to try and help us do some hardening. We found that we're going to really need that. There is lots of incoming from Russia, the UK, a lot of things bouncing around, and the IDS snort logs are very full, very fast, and we should have a lot of fun doing that. And there's more options too. Right now it's running through a pfSense box. Might want to try a few different options. We've got an India box, an open sense. What were the ones that we were using? Palo Altos. We've got the Palo Alto VMs, so we can try and get the different firewalls set up, different VPN configurations. Some Windows domains. We've got some people interested in setting that up, so we'll have a domain within there and use some of the networking. With the cluster too, it does power management on the server, which was something I thought was pretty cool. It can actually turn on and off the servers depending on need and who's logged in. That was something I learned this week that I thought was pretty nice. Sure what else to fill with 5 minutes of server talk. I'm a little sweaty and dirty from moving stuff around. And
Did you configure a server? Config a server?
Config a server? Well, we'll have that available too. We've configured it. Basically, right now I just have the control server, the firewall, and the ESXi running on bare metal, obviously. And then the control server now has those on a cluster, which what I want to dive into deeper is figuring out how to get things to move smoothly across the processors and RAM.
1 minute.
And could really use some help. Tonight, actually, I need at least 4 people to help me move a rack out. Actually, I need 4 people that I can supervise moving a rack out, because I already kind of threw my back out, because we have to tip it to get it out the door. And I really appreciate your help. And any questions?
What's the biggest challenge you've run into so far with this project?
Well, personally, getting the firmware updated on the Dells, there was a bunch of hoops to jump through. So that was more of a challenge than I expected. I've done it before. It reminded me why I've been looking for other career options besides being a sysadmin. I enjoyed it when I was able to, and it's a nice nostalgic feeling, but that's not what I want to do every day. Other challenges too is just diving into something new. VMware is vast, and we're trying to use as much of it as we can without having an expert to consult with right now. So hopefully we'll be, since we're running as a club and then as a group for this class, we'll be able to pull in some people for talks for the club and stuff to get the VMware going. Okay. That could be more enough of your time. So.
Yeah. 4 people. We need 4 people.
Yes, yeah, the 4 people. Any volunteers?
For like 10 minutes.
I got Tony, I know. Anybody else? Yeah. All right. We'll see you guys over there.